This is lecture 32. Last time, after we discussed memory virtualization, we introduced the notion of a fixed size memory block, so similar to the 8-byte blocks in Xenu, that allows us to shrink the table that's needed to perform address translation. So this per process. Let's make this thing a bit bigger. So this per process address translation table, as is, would in our example architecture, which is our 32-bit architecture on x86. So this, used as an example, would require this main memory, which starts at 0 and ends logically at 4 gigabytes, since that's roughly 2 to the 32. We have 32 bits available. And we would need to be able to then translate every address, which is virtual, which is fake, into its true physical address, the actual physical address. So the true address, which means physical address. And we would need to have a table that is pretty much of the same size. So it needs to have about 4 billion entries. So this table would need 4 billion, roughly 4 billion entries or rows. And that's too much because it's per process. And in this case, one simple technique that we can use to shrink this down further is to use this fixed size block. So fixed size block, and it can be different number, but we are using a very popular size, which is 4 kilobyte. So it's about 4,000 bytes big, 496 to be precise, but roughly 4K. And when we do so, obviously the gain is that this table now can shrink, since this 4 gigabyte space is now being referenced using this very coarse. So this is a much coarse granular way of addressing memory. So we divide this thing by 4 kilobytes, which gives us roughly 1 million entries. So 1 million entries. And that's of course much smaller than the 4 billion entries that we would have needed, and that would have been just for one process per process. With hundreds, with thousands of processes, this just of course becomes too much. Even with this shrinkage of having 1 million rows, it's still a lot. So what still remains to do is to shrink it even further, and as I mentioned, to compress it. And how to do that we will discuss later. After we get all the big picture items into place, then we will talk about some additional details, such as further compressing it. And this is a must. So it's not an optional thing. It must be further reduced. And we will see how to do that. But before we go into this, let's just make sure that we get this thing here wrapped up in terms of what implications this has. So this fixed size block, in this case, as an example, again, they can be bigger, they can be 16 kilobytes, they can be even bigger than that. But these fixed size blocks, they are referred to as pages, a page. And when we use such an approach, then we also call it paging. So the unit is a page, which is a fixed size block, and by default, we will assume it's 4 kilobytes to be concrete, to make things grounded in our 32-bit architecture. And once you understand that for 4 kilobytes, then it's easy enough to generalize for any other size. So just making sure that you know for one particular size and be specific and concrete. That will help understand the more general cases, of which there are others, like for example 64-bit architecture. But all stems from knowing how this is done. So with this structure, what it means is that our main memory, this guy here, I'm showing it in the smaller scale. So this is our main memory, which was looked at earlier in units of bytes from 0 byte to 4 gigabytes. So that's a logical depiction. Now that's going to be the same memory is now going to be sort of abstracted and looked at in terms of these 4 kilobyte chunks called pages, these blocks of memory. So here is the first page, second page, third page, fourth page, etc. And then the last page is roughly the 1 millionth page because of the saving that we mentioned. So this physical memory here, or this memory, is going to be viewed in terms of pages, and we index these pages by their page number. And in computer science, by default, we start with 0. So we start with page 0, page 1, page 2, page 3, and then the last page is, of course, 1 million, roughly speaking, 1 million. Of course, when we access content, we are still interested in bytes, in specific bytes, or bits, or words. But by default, byte is a good unit to think about. So when we are trying to fetch the content of some specific byte, that is this way of looking at the same memory, or this way of looking at it, then by having these pages, to access a specific byte, it entails 2 steps. We first need to know in which page is this byte located. So which page is it, say in this page? Maybe this is the 99th page. So we find out which page this byte is located. But each page has 512 bytes. So in this case, step 1 is to find out in which page this specific byte lives. And then we have to determine within this page, so within a page, where is the byte? So we have a 2-step process. Which page? And then of course within the page, which of the 1200 bytes which are housed in one specific page. So it's a 2-step process to keep in mind. So how would we do that? By default, again, in the absence of this further optimization to compress, so we will talk about this issue later, what it means is that, again, using x86 32-bit architecture for our backends with 4 kilobyte page size, which is very common to make things concrete. So using that as the underlying assumption of the hardware, what we are now going to do is there is an address that's part of an operand of some instruction, as we discussed, and that address is going to be virtual. It's not the true physical address because we are doing indirection, i.e. through address translation, the stuff that we discussed. And assuming that we have this size, 4 kilobytes means so this is 4096. So now we have to be here precise. That's going to be 124 times 4. And that's going to be, so this is about 1,000, that's 2 to the 10. And of course 4 is 2 to the 2, so this is 2 to the 12. I could have just said this is of course 2 to the 12 because we do it all the time, but just to spell it out once so that we're all on the same page. So to note which byte we are interested in within a given page, we need 12 bits because there are these many bytes that reside within a given page. That means that if this is the address, which is 32 bits in our architecture, then we need to have here 12 bits that are used, so 12 bits that are used to specify which byte we are interested in within a given page. So these 12 bits are used to identify what we term as offset. So within a page which has 4 kilobytes, there's one specific byte that we're interested in. Where is it located within this 4 kilobytes? That's like an offset. And so these 12 bits are needed to identify that. These remaining bits, which are of course 20 bits, since it's 12 plus 20, which is 32, these 20 bits, are now used to identify which page we are talking about. So these 20 bits identify or are the page number. So we said there's a two-step process. First, we need to know which page we're talking about, and then after we do that, we need to know which byte within that page. That's step B. So the step B needs 12 bits because of our 4 kilobyte page size, and then the bits remaining is 20 in our 32-bit architecture, obviously. And so therefore, these 20 bits are then used to denote the page number. Which page are we interested in? And 2 to the 20 is how many? That's 2 to the 10 times 2 to the 10. And 2 to the 10, of course, is 1024, or roughly 1,000. That's why I refer to this as 1 million, because it's 1,000 times 1,000, which is roughly, in this case, 1 million. And here we're not paying attention to those details of there being, of course, 24, which we have to do when we do actual calculations. But ballpark speaking, it's about 1 million pages. So, what does address translation then actually entail? So we have a virtual address So here's a virtual address X, which is going to be 32 bits long. So it's going to have X31, X30, X3, X2, X1, X0. These are the bits. These are the 32 bits of X, which is a fake, which is this virtual address, because we are now giving the illusion to every process that each process owns the entire memory. That's what we discussed earlier. This is the property 2. Property 1 was dealing with external fragmentation, and this property 2 was providing this illusion of each process owning the entire memory, called virtual memory, which of course simplifies programming. These are the two main benefits that we discussed. We are now soon going to discuss the third benefit, called hierarchical memory. So we are going to come to that in a short while. But just completing this discussion of address translation, this virtual address now needs to be translated to some address Y, which is, so it's going to be the actual physical address. So this is the physical address. That's Y. So this is the true physical address. And of course, it too has 32 bits. So Y31, 30, and this is the least significant bit. This is the most significant bit. That's how I'm going to write it here. And then Y3, Y2, Y1, Y0. These are the 32 bits of the actual physical address. But we said that here we are using 12 bits to identify the offset. That is to note B, which is where in the page is our byte of interest located, the offset. And these remaining 20 bits are used to identify which page we're talking about, aka the page number. Which means that in this setting, if we are using the lower bits from the least significant bits up until X11, these are now 12 bits. If we are using these 12 bits for offset, for B, and we're using these remaining bits, X12 until X31, that's the page number, A, then these bits from X12 until X31, these guys must be mapped to different bits, Y12 until Y31, because the page number is going to in general change. However, the offset, these guys, Y0, Y1, Y2, 3 until Y11, they don't need to change. That is, this is the same as X0, Y1 is the same as X1, etc. These can just stay unchanged. And that's because when we are going to map from this page number, say this is a virtual address and its page number is say 50. And address translation now says, okay, this page number is actually page number 101 in the physical memory. So that's the physical memory. Then that means this must be changed to this, which means these 20 bits, X12 until X31, must be translated to these 20 bits, which is Y12 until Y31, because their page numbers are different. But within the page, that is within this particular page, the byte of interest, suppose it's the first byte, just as an example, that position is the same here. This position of the byte of interest within a page is clearly relative. It's not absolute. And because it's relative to a page, this information did not change. It doesn't need to be translated. It is just what it is. And so we have the benefit of just leaving these 12 bits intact during address translation. That's our address translation here from virtual address to physical address. The only thing that we need to change are the higher order 20 bits. These 20 bits must change to these 20 bits, which is tantamount to saying that this virtual number, suppose this virtual address given by this page number in the virtual address space is now translated to a different page number in the true physical space. And that means here the last 20 bits need to change, but the first 12 bits don't change. They just remain the same because they denote the offset within a page. And the offset, of course, does not need to change. So keep that here in mind. So going further, what we have is that we have this 32-bit pattern, which is an address, but it's virtual, and now we're going to translate it using this paging architecture into a physical address that's also, of course, 32 bits big. But what we now know is these 12 bits don't change. They remain the same. It's these 20 bits that need to be translated. And so, when we talk about our address translation table, which under paging, so using pages, we call this structure generically a page table. And inside this page table, the content, that is, what bits get translated to what bits, is 20 bits get mapped to a different 20 bits, because it's only these 20 bits that we need to translate. These 12 bits here, they remain unchanged. So the content of the page table in our setting needs to only be 20 bits wide for this to be translated to this. And this is referred to as page number. So this is a number. These are, of course, bits. Numbers are bits, so therefore it's the same thing. But we are translating a page number in the virtual address space to a page number in the physical address space. So this is what we have to carry out. And this page table, this address translation table under this fixed size blocks of memory called pages, where are they located? We are going to assume that we can keep them in our main memory. And these page tables are, as we know, per process. Every process has its own page table. So here, this may be the page table of process. So this is the page table of process P5. How big is this page table in our default case? It has 1 million, roughly, entries. That's the table, as we discussed. The page table of some other process, suppose process P9, that might be located down here. That's where the page table, P9's page table, is located. This is this guy's page table. And when now we are using all the knowledge that we have from our prior study, when we now add scheduling to this picture, and we are going to context switch. So suppose P5 is current, but now we are going to context switch this guy out. So this guy is going to be, here's our CPU, and this guy is going to be context switched out, and we are going to context switch in another process, suppose P9, so that P9 becomes current. Then when the CPU here runs, it needs to be able to know where the page table of P9 is. When P5 was current, its table was located here in memory. Now, when we context switch, the hardware needs to know where P9's page table is, so that when P9 executes instructions, and these instructions have operands, and those operands may be addresses of main memory. In that case, this guy needs to be able to, with hardware support, translate from virtual address to physical address, and that's done through this page table, as we discussed, this address translation table called page table. And so in today's computing systems, to keep track of where the page table of the current process on a specific CPU is located, there's a register, and that's no surprise since we have seen this technique before. So there's a register. So there's this register that's built in as part of the CPU for this process, for this purpose, to keep track of where the page table of the current process is located. And this register is generically referred to as, let's see, page table base register. So PTBR. So this is a very generic name, but it means page table B base register. So this is the important one. And so this guy, when this guy was current, was pointing to this address in memory. That's how the CPU knows where to find this table, because its job is to perform, with the help of other hardware support, this translation from virtual to physical. But how is it done? Through lookup of this table. So this is a table lookup. And this table is a software construct because it's just a data structure that resides in memory. But like with, in the context of x86, we noted two very important tables, GDT for marking user mode, kernel mode, and IDT for installing interrupt handlers. And the CPU knows after the software, the OS has configured this table, so this is purely software, but this piece of software, this data structure, is a data structure that the hardware also needs to know about. And so we said that in x86, as an example, there's this register called GDTR, so that's the register, which points to in memory where this table called GDT is located. So there's another register here which we discussed, GDTR, which holds this. And the same goes for IDT. And of course, this needs to be configured once when we bootstrap and when we then initialize the kernel. So it's done once and then it doesn't need to change anymore. But the content of this register, this page table based register, this guy needs to change each time we context switch in and context switch out a process. So when this guy was pointing here, that was when P5 was current. But after this guy is context switched out, this guy now cannot point here anymore. It must be made to point to here because that's where P9's page table is located. So as part of the context switch routine, as an example in Xenu, there's more stuff that needs to be saved, restored than prior, and this is just part of the picture. So context switching thus accordingly becomes more complex due to all of these added chores, tasks that we need to perform. So setting up and changing the content of this is as important as changing the content of the stack pointer ESP in our backend machines that we needed to then change to point to the stack of the new process from beforehand pointing to the stack of the old process. And of course, in a similar vein, the same thing must happen for this register. So it's all under the purview of scheduling. That's why all of the subsystems are interdependent. You change something here, it's likely you have to make changes elsewhere because there's all this dependence going on. We are trying to isolate them separately, and we are trying to talk about each piece separately to the extent that it makes sense to do. But as you can see, when so doing, we always have to leave things out, and we have to keep it like a black box, and then we open up that black box later on. And here we are seeing further dependence between scheduling, which is part of process management, and this paging, which is part of memory management. Two entirely different subsystems, but very much dependent upon each other because changes in one affect the other. Now, all of this part about using page tables and then translating these addresses will become more complicated because we have to compress or shrink the page table because it's still too large. It has 1 million entries per process. We need to shrink this thing down by a whole lot, and we are still going to then see how to do that, and that's going to make this picture more complicated. But the starting point is what we just discussed. That's the big picture. So keep in mind how everything fits in and how this per process page tables come into play when context switching. And even that is not done because we will see that there are other dependencies that come into play that are even more important than the stuff that we discussed. But they all build on the stuff that we have discussed till here. So keep that big picture here in mind. Next item that I noted we need to discuss is number 3. That is, when we jump the gun and we are now utilizing this hardware support to perform indirection, we said that there is this third benefit that was referred to as memory hierarchy. So what is this guy? Memory hierarchy. This feature is another super important feature of modern computing systems. It's a key essential feature that too tries to provide an illusion. So the fact that we have virtualization technique that we used that provides an illusion of each process per process. So each process for memory, we provide the illusion that they own the entire memory. That's the illusion. So that's under memory management. And then per process, we provided the illusion that they own a CPU, which was under process management. Here we are going to now provide an illusion, which is an illusion of the type that relates to performance, speed. And of course, this performance was a key theme throughout the course. We said that we want to always get constant overhead. That's our goal. And only when there's absolutely no other way do we then go to logarithmic and sometimes linear, because linear cannot be avoided, like copying cost as we discussed, but not for priority lists which are linear. Those we can make logarithmic. So what is this illusion that we're trying to provide? For this we need some background, and here is the background to keep in mind. So here is our CPU, and we are by default dealing with one CPU for our backend, but all of this can be readily generalized to multiple CPUs. So make sure to understand for one CPU, then the multiple CPU case is a fairly straightforward extension. So far, we dealt with hardware comprised of CPU and main memory, or just memory. And that's what we are here focusing on now. And we will also talk about disk, where we store permanently files. And in today's technology, two types of disks are popular, the hard disks and SSDs, which stand for solid state disk or drive, and they have different properties, and we will talk about their main differences when we discuss file systems. And that's going to be the last main topic of this course, discussion of file systems. And they live on either this type of hardware or this type of hardware in today's environment. And there are some significant differences in terms of file system design and implementation depending upon what underlying hardware it uses to store its content. But for the moment, we won't discuss much about disk in detail till we reach here, but we will talk about disk a little bit in the context of memory management. So that's now, because it does play an important role when we discuss memory hierarchy. The term hierarchy probably hints at the fact that there is sort of a different hierarchical scheme of memory going on. So here we have two types of memory: main memory, our RAM, our random access memory, quote unquote, and our disk, which is kind of a parallel sequential memory, but it's not random access memory. So, we should not forget that the fastest memory are registers on our CPU. So here are our registers for our x86. We had EAX, EBX, ESP, these guys. So these are the fastest parts. So the starting point of this discussion is our address translation tables. They live here. We could, so they live here. Now, that was our assumption. And we now look at today's typical hardware, and we are going to consider the overhead, the access speed for some instruction to access, to read write to a register versus to main memory versus to disk. What's the gap in speed, loosely speaking? To be technical, we have to check, are we talking about cycles? Are we talking about time? There are lots of other details that one has to specify to make precise technical sense. Here we're talking about operating systems, and this is just a conceptual overview, and we are not going to delve into more details about hardware per se beyond what's needed to make work in terms of what's needed for OS. So when we compare the time that it takes for a move instruction to access content in some register on the CPU versus accessing content in our main memory, if this is, say, 1, it's also noted 0 sometimes. Again, it doesn't matter for this purpose. Then the time to access main memory is, ballpark speaking, on the order of 100 slower. Is it 100? No, it can be 50, it can be 75, it all varies. So therefore, these are just toy numbers to give a rough ballpark sense of the gap in performance when one tries to access content that resides in a register versus at a memory location. So here's a register here, and here is its content. That content may also be resident in this memory location at some address. What's the time that's required to fetch, to read or write this content, depending upon where it's at? If this is 1, this is, ballpark speaking, 100. So this is way, way, way slower than this guy. What about disk and main memory? I'll use hard disk as the main reference. SD is faster, but I'll use hard disk, which is still used mainly on servers and such. So suppose this main memory is our reference point. So we call main memory 1. Then relative to main memory, how slow is disk? By about 1,000. Again, ballpark speaking, all of these numbers don't make any specific sense. It varies from architecture to architecture, from device to device, from year to year, but ballpark numbers to give you a sense of the magnitude that we're talking about. This is 3 orders, this is 2 orders of magnitude gap relative speed wise from memory here as registers on the CPU vis-a-vis stuff here in main memory. Could be higher, could be lower, but that's the gap. Huge gaps. So if you can put something in main memory, you don't ever want to go to disk because it's going to have a huge performance hit. If you can put something in registers and then you can just keep them and you can avoid going to memory, that's the way to do, because you go to memory, you are going to pay a huge penalty to our main memory to pay a huge penalty to make it work. And if such were the hardware configuration of computing systems, they would still be very, very slow because we have only a few registers, so much has to be here. And what cannot be kept here may have to be kept here. But this guy then would be the next fastest guy, but this guy is still much slower than the access speed of memories on top of CPU. That's why we need caches. Caches are faster memory. Faster than what? Vis-a-vis our main memory. That's going to be our reference point. So we are going to not even mention disk in this context. This will come into play for a different reason. So you will have heard, hopefully, that there are different types of caches called level 1 cache. Level 1 cache, typically written L1. Level 2 cache, L2. Level 3 cache, L3. And there can be even more levels. 1 means it's fastest among these caches. Then 2, then 3. So the smaller the number here, so we go toward level 1, it becomes faster. But this faster guy comes at a trade-off. It's costlier and therefore it's smaller. So it's faster, that's good, but the capacity of this memory is smaller. Of course, that means that when we go from L1 to L3 or higher, then it becomes slower, but it becomes larger. So it's a trade-off. Large, slow. Small but fast. That's this idea. But it doesn't have to stop here. This idea of caching can extend to the entire picture. So the entire picture is here from registers all the way to disk. And is it only at disk? No. We still use today tape drives. So here at Purdue in Computer Science Department, we do daily backups. These are called incremental backups, which are stored on disk. So for example, if you created a file about a week back and then you purely accidentally delete the file, you can then ask our system staff to restore the file because that file has been backed up. But after some month, and these things change, the content of this disk is backed up to tape. So tape backup is still a common technique that's used in today's systems. We will not discuss tapes in operating systems, although they are still practically relevant. So our borderline will be right here. Are tapes therefore the last resort? No. Even in today's environment, where you have, for example, all of the sort of popular technology under cloud computing, clouds or data centers, they all mean the same thing. Internally speaking, just focusing on different parts. If you have, for example, a company that whose data is located in some city, in some data center which houses some cloud computing system, and they have a reason to physically move these data, these bytes, from this place, suppose Atlanta, to suppose San Diego, which is quite a distance. Then you might imagine that with all the high-speed networks that we have today, that we can use internet protocol, stuff that you study in CS422, to ship these bits very quickly from here to there. Not so. With such huge amounts of data that are stored in these data centers, we're talking huge amounts. Tera is just a tiny bit. The fastest way today to ship this stuff is by truck. So you put these boxes, these computing boxes, onto a truck, and then the truck moves at a slow speed and goes here, and that's the fastest thing to do. About 20 years back, when we had a bunch of supercomputing centers here all across the US, and researchers needed to send at that time massive amounts of data, gigabytes of data, possibly terabytes, but not at the level of what we have today. Then at that junction, people were building these high-speed networks, but they were still not fast enough to ship even those volumes of data then. So what did people do? They put the data on tape drives. I just mentioned tape drives. And then they used carriers like USPS or UPS or FedEx to ship them physically from one place to another. That was still the faster way to do. That got solved eventually, and now they can use for data in terabyte range the networks, and that'll just take just a few minutes perhaps to complete. But for volumes of data that we are storing today in clouds, in data centers, again, moving them physically, that happens to be still the fastest way. So keep all of this big picture background in mind so that you don't think that we have solved all these problems and trucking or such is unnecessary anymore. That is far from the truth. It's a fairly complicated but also interesting world. Anyhow, going back to here, the buck will stop at disk. So we are not going to go into this domain at all. It's not the purview of OS. We are going to stop at the disk. But we are going to take the viewpoint that it's a layer, it's a hierarchy of caches. Fastest, so this is fastest, but smallest. We have only a few registers, a bunch of them, but just a few compared to all of these other guys, but they're fastest. On disk, I'll fix hard disk so that we don't have to keep dragging in the differences between SSD that we will talk about later on. For hard disk, it's the largest, but it's slowest. Slowest and largest. Main memory is slow. Certainly much faster than disk, but still slow. But it's large. And it's of course much larger compared to these registers. So there's too big a chasm, too big a gap between these layers. And a computing system that's built with this in place would really be too slow to be of much practical use today. These caches L1, L2, L3 that fill this void, this gap, are absolutely needed. So what we're talking about is here, we're putting the fastest but the smallest cache L1 close to the CPU. Typically, these are actually part of the CPU's real estate, so they're on board the CPU. Then, further removed but bigger is this L2 cache. And further removed and bigger is our L3 cache. And if we have this L4 cache, it would be even further. But there's this hierarchy of faster, smaller in this direction and slower but larger in this direction. That is this hierarchy that we're talking about. Okay, so now the question is, so what? Why does this help? Why would it help to insert these 3 layers of caches? And I'm going to simplify it down to 2 because for 3 the same reasoning applies and I don't want to clutter it too much. So we'll talk about 2 layers, L1, L2. So what benefit does this give us? This is going to be small, tens of kilobytes, possibly a few megs. It's in that ballpark. This is 8 gig, 16 gig, 4 gig. The new iPhone 12 has, I think, 4 gigabyte of RAM. The iPhone 12 Pro, I think that guy has 6 gigabyte. Not a lot, but anyhow, that's the ballpark size of this guy. These guys, in terms of size compared to that, are tiny. So what benefit do these tiny memories here, which are much faster than the main memory, have in terms of performance? What benefit will they bring with respect to performance? I'll come back to that in a second, but to complete this picture, what is the rough, again, ballpark speed difference? Like this was very crude, very coarse ballpark difference between CPU that accesses registers and this L1 cache. It can be anywhere from close to the speed of registers to a factor of 5. I'll just use as the reference point 1, a factor 5 difference. Again, these are not meant to be numbers to be taken literally. They are just giving you a sense. L2 compared to this guy, that is L1. So making this guy to be 1, this guy is also going to be 5 times, ballpark speaking, slower than L1. So L2 is roughly about 25 times, because it's 5 times 5, slower than registers. And here we have 100, so how do we get to 100? If you have from here to here, say by a factor of 5 again, roughly. So if this guy is 1, and then what is this guy? Suppose it's a factor of 5. Again, I left out this L3 and other layers just to simplify things. Then you see that, oh, this is a factor of 25 times 5. So therefore, it's about 100 and some change. So roughly ballpark, it fits into the picture. But the rough rule of thumb that you may use, keeping in mind the big caveat that these are really only numbers to get a sense of the magnitude differences. You can say going from this to this, we have a slowdown of a factor of 5. From here to here, we have a slowdown of a factor of 5 and such. That's roughly to view. And when we go from RAM to disk to hard disk, we have a factor slowdown of about 1,000, 3 orders of magnitude, a huge gap. So now to the important point. We are trying to give the illusion to processes. So it's all about giving this illusory world effect to processes, that they own the entire memory, that they own the entire CPU, when in fact they have to share among all these guys, but each one thinks they are the owners of the memory. Here we're going to give a process the illusion that it actually is owning memory at the speed of L1. So it's not quite register, or it's very close to register speed. And we're going to give the illusion that this memory is not only super fast, but it's actually much, much larger. We're going to give the illusion that this memory is fast. So that is not an illusion, it is fast, but it is small, physically, but we're going to give the illusion that this memory is actually very large. That's the performance aspect that we are going to provide through this memory hierarchy. This is a hierarchy. These are the levels. RAM is a cache. We are going to view the RAM as a cache. Disk is a cache. Everything is a cache. It's a hierarchy in memory, and it depends on where you are, at what level. That determines your physical size and your speed, your performance. So with that in mind, now let's go to the essential part, which is when we have such a memory hierarchy, and our worldview is one of multiple levels or layers of caches, from registers to L1, L2, we're leaving out L3, L4, etc., to main memory, I'll just call it RAM, roughly, to disk. They are all just different levels in this hierarchy. Fastest, smallest, slowest, largest. But why does adding these guys help in terms of performance? The reason is for the practical empirical fact. So there's an important empirical fact that real world applications, so we're talking about real world processes, and you encountered some of these concerns when we did scheduling, where we talked about CPU bound processes, IO bound processes. These are all the things that make scheduling to be very specific and unique to operating systems, because scheduling is not unique to operating systems, but it is these considerations of the property of the behavior of real world workload, as we call them, that makes OS scheduling different from other types of scheduling that we use for packets and networks, etc. Here, in a similar vein, an important finding over many years is that in real world environments where we have processes being created that are running apps of different types, for the most part, they tend to obey an important property called locality of reference. What that means, basically, roughly speaking, is that so we have code, that is instructions, and we have data. But for both instructions and data, what holds true is if the CPU is now running this code and this piece of data, and I'm showing it at different places, then if it's accessing this instruction now and it's accessing this piece of data now, then again it is likely that it will access this same instruction and the same piece of data in the near future. Locality means it's local in space, space meaning memory. So here is the code, start till finish, and here is this local area where the current code is located, and it has its neighborhood, code close by. It turns out that when we have real-world apps that are running as processes, then they tend to repeat the same instructions within this window again and again and again for a long while. And when these instructions are repeating, then they tend to access the same data within a window again and again and again and again. So this reference means to access. Locality means in space. But it's not just space, it's also time, because as time is progressing, the same instruction is being used now a bit later, a bit later, a bit, over this time window that is local in time, the same instruction gets reused again and again and again. And the same goes for data. So from a space viewpoint, that is, where in memory are they located, it's local. And from a time viewpoint, they tend to be local. They don't have to be local always in space. Maybe it goes here, it goes here, it goes back here. So these things can always be violated, but overall speaking, generally they obey this locality of reference. That means that although this piece of code is fairly large, this data is fairly large, over the course of time, so this is time, here the process was created, so the process is created, and here the process terminates, the app terminates. So during this time period, the process is alive. And when it's running on a CPU, so it becomes current on a CPU, it fetches, decodes, and executes instructions, which then reference memory for data, etc., etc. And it turns out that over a piece of time window here, it's very likely that the same set of few instructions, the same few data items are going to be repeatedly needed during this time window. After some amount of time passes, maybe the code will switch to other instructions. So maybe during this time window, a few other instructions and few other data items are needed during that time window. So this doesn't stay constant, or it doesn't have to stay constant throughout the entire lifetime. It can change from here to there. But this time window is fairly large in terms of the time scale of what we are talking about. And during this time scale, a process based upon real world observation has this property of locality of reference. What it references, instructions and data, tend to be localized, and that means that because they are localized, there are few, not many. They can be stored in small bits of memory, which means you can put these guys that are now being accessed in this small but super fast cache here. Typically we have two types of caches, to store code and to store data. So L1 is very fast but small, but by locality of reference, if we are able to keep them around here, then when the CPU undergoes fetch, decode, execute, once these few instructions have been loaded into this fast but small cache, and these few data items are loaded here, the CPU just needs to go to L1 and it finds them here. We call it a cache hit. If we don't find it, it's called a miss. And you know that from computer architecture, we're just repeating here. And then if it's a hit, and with high likelihood, high probability, if it's a typical real world app, the hit rate, the likelihood of hit is very high, 90-some%. So it finds it here, and then it's able to fetch it and then run. It doesn't need to touch this memory, which is lower. It doesn't need to touch RAM. It doesn't need to touch disk. So for a while, until there's a miss, and maybe different instructions and data are then needed for a while, until such time, the CPU operates as if everything is available in this super fast memory, even though it's very small. And it makes perfect sense only because the real world has this property of locality of reference. If we were to live in a world where this is not a property that programs obey, then having L1 cache and L2 cache is just not going to be useful. Why have these tiny bits of fast memory when you are jumping all over the place for your instructions. It's random. There's no pattern. There is no locality. In that case, having such a memory hierarchy is of little to no use. But because real-world workloads obey this very strong property, achieving this memory hierarchy or building it using hardware support is of significant benefit. Okay, so good, but how does this relate to virtual memory? And that's going to be the last comment here. One reference model that we are going to consider when we're talking about virtual memory, so that's our discussion here, and we're talking about the benefit of number 3, which is this memory hierarchy. But how does it relate to this illusion that we gave to every process that they own the entire memory? Well, the instructions here we are going to assume are going to access memory, which is using virtual addresses. So this guy speaks virtual addresses. And we are going to assume this does not have to be this way only, but this is a very common architectural reference. So we are going to assume here that when we store the instructions and data that we recently used inside this fast but small cache, we are going to store them using virtual addresses. So they are kept virtual. So this CPU looks for the next instruction inside this cache, L1 cache, and it looks for it in terms of its virtual address. Same for data. And if the hit rate is high, it's highly likely to be here, then it finds it, it's then able to do its work again and again and again. And hence, it runs at the speed almost as if all of its memory was super high speed L1 memory, although this L1 cache is tiny. Moreover, because it's virtual, what is not needed? No address translation is needed. So this is the specific item that we want to focus on here, because we're talking about virtual memory and we talked about having to translate virtual to physical addresses. But once they are kept here and we can reference them using virtual to virtual, everything is virtual. This guy lives in this virtual world. L1 cache, under the assumption, lives in this virtual address world. They speak the same language. There's no need to translate virtual to physical. So all of this stuff about performing address translation with hardware support still results in performance penalty, even with hardware support. But by having everything be localized here, and the CPU speaks virtual, L1 cache speaks virtual addresses, they live in this virtual world, and if you have hits, no need to engage in any address translation. It's a huge benefit. So we will stop here.